welcome everyone. Good morning or afternoon, wherever you may be in the world. Welcome to today's PV Tech webinar. My name is Ben Willis. I'm the editor of PV Tech, and I'm delighted to be your host for this session, which is brought to you in partnership with our sponsor today, Trinasolar. As the solar industry enters its terawatt era, the pace of technological innovation has never been more critical. The global solar sector is experiencing unprecedented growth, with utility scale installations driving demand for modules that deliver not just higher power output, but also superior efficiency, reliability, and most importantly, lower levelized cost of energy, or LCOE, as we of course know it. In this rapidly evolving landscape, manufacturers are racing to develop next generation technologies that can meet the dual challenge of maximizing energy yield while minimizing total system costs. The stakes are very high. Every percentage point improvement in module efficiency, every innovation in cell architecture, and every advancement in manufacturing capability directly impact project economics and the speed of the global energy transition. This brings us to today's webinar. Trinasolar, a global leader in PV manufacturing, has consistently pushed the boundaries of solar technology. Trina's latest breakthrough, the Vertex N G3 module, represents a significant leap forward in addressing the industry's most pressing challenges. Today, we'll explore the key technological characteristics that define the Vertex N G3 platform and how these translate into tangible benefits for utility scale projects. Over the next half hour or so, our expert speaker from Trinasolar will guide us through the technology trends shaping the solar industry, the core technological innovations behind the Vertex N G3 module, and how these attributes can deliver a step change in project economics across a diverse range of applications. Before we get underway, a quick reminder that this webinar is interactive, so please use the Q&A function on your screen to submit your questions throughout the presentation, and we'll address as many as possible during our dedicated Q&A session at the end. So without further ado, I'd like to introduce our speaker today, Rocky Lee, who is a global product manager at Trinasolar and will be our expert guide through today's topic. So Rocky, over to you. Thank you very much.
Okay, thank you, Ben. Thank you for having me. I'm very happy to be here. Hello everyone all around the world. And today I will bring you our Trinasolar's Vertex N G3 next generation innovation for lower LCOE and higher yield. So today's presentation will mainly come from two parts. So the first part is a quick outline of who we are, Trinasolar overview, and then secondly, we go into the introduction of our Vertex N G3 new product. So for Trina, we founded in 1997, almost 30 years history, and we are not only the top tier solar manufacturer, but also we are committed to becoming the global pioneer in smart energy total solution provider. And we have 7 corporate or regional headquarters across the globe, and our business covers more than 180 countries over the world. And by this year's January, we've already got 38 world records for the PV module and PV sales, and also our cumulative module shipment by the end of last year is exceeds 320 gigawatts. And our business cover quite a wide range. We can offer smart energy solutions for utility, C&I, residential, and we can also offer the products like module, energy storage, tracker, and also we can also offer the product solutions. And today we focus on the module. For Trina, we are the pioneer for 2 10mm size large wafer module. Our branding name is Vertex. Vertex series, and the cumulative shipments for the 210 module, we are ranking #1 around in the world, and for the N-type technology, we have 500 more of the patents. And in terms of this large wafer 210 millimeter size module, we've already achieved 236 gigawatts globally, cumulative shipment. And also we can offer different product settings for different application scenarios. And then let's specifically look into the key topic today for the Generation 3 new product introduction. This is also a new product based on our 210 millimeter wafer, also N-type and TOPCon platform. So we bring you our latest portfolio here, as you can see in this page. So now for the Generation 3, the product name is, we add a suffix G3 at the very bottom of our branding name, represent that is TOPCon 3.0 or Generation 3. And we have 3 different format designs. So we, from the left-hand side to the right-hand side, it covers different application scenarios for the residential, C&I, and large-scale ground-mount power plant. And for the small format modules with G3, we can increase the power to 485 watts. And then for the key topic for today is our medium and large format module, Vertex N G3. For the medium-sized module, the industrial standard size, we can achieve 670 watts. And for the large format module, we can achieve 760 watts. And in terms of the roadmap for the Vertex N G3, actually these 2 modules will be introduced by the second half this year from Q3. And just like what I mentioned, the highest power is one is 670, the other is 760. And we can achieve around 15 to 20 watts power increase compared to our last generation. Our current generation is Vertex N, it's also the second generation. And also one point to mention that our new generation would be a supplement for our current product portfolio. So which means once we introduce the Generation 3, the current generation with the current Generation 2 Vertex N and the new generation Vertex N G3 will run in parallel altogether. So which means that they will coexist with each other. So if you have some more cost-effective, lower power requirements, you can still choose our Vertex N series. But if you have high efficiency module requirement, you can choose this new Vertex N G3 product. And then what are the new features for our Vertex N G3 modules? And then here we outline the overall benefits for these 2 modules. So first thing is that we can deliver the exceptional power and efficiency, just like what I mentioned. This time we can increase 15 to 20 watts power increase compared to the last generation, and the module efficiency exceeds 24.5%. And aside from more power density, we can also offer better power production or energy production, energy yield capability. So mainly from 3 aspects. The first is we optimize the performance in terms of the the temperature coefficient. It's upgraded from the previous generation 0.29% to the new generation 0.26%. And secondly, we can guarantee you more power harvest during the lifetime. We can offer you better warranty. Specifically for the annual degradation, we can offer you better from last generation 0.4% to this new generation 0.35%. And these 2 points is very tangible, but also there's some underlying benefits. Is with the TOPCon technology, you can have better energy yield in terms of the better bifaciality and the low light performance. These 2 is some underlining that maybe not very tangible, but I think is very critical, especially for the large scale ground-mount power plant, which I will elaborate a little bit further in the upcoming slides. Okay, let's look at these features one by one. So first, let's look at how we can achieve more power density with the same module size design. So basically, this time we adopt this high density packaging or high density interconnection plus multi-cut solar cell technology. So we do the side-by-side comparison here. On the left-hand side is our current generation Vertex N. On the right-hand side is our new generation Vertex N G3. As you can see, we have two primary upgrades. The first is we eliminate the cell gaps. So as you can see, the left upper corner, the previous generation, the cell between cell, there's still spacing. So right now, with the G3, we eliminate the cell gap. We adopt this overlap gapless design. So which means with the same module areas, we have more active areas on the module side, on the module surface. And the second thing is we upgrade from the previous half cut technology to the 1/4 cut technology. By adopting these technologies, it can reduce the current for each solar cell. And then if you consider the module internal loss, I squared times resistance, so then the internal loss can reduce by 1/16 compared to the previous generation. So by this means, with more active areas on the front side and less internal loss, then you can achieve higher front side power and higher front side efficiency. And aside from the cell technology, module technology from the solar cell side, we also have some upgrade. So the first thing is the multi-cut plus edge passivation. The edge passivation is a very important technology to be paired with the multi-cut technology, because once you slice the solar cell into more pieces, you might introduce some new defects alongside the cutting surface. So which means there would be some potential recombination recombinations alongside the cutting surface. So then we introduce another cell processing technology, is the edge passivation. After the slicing, we do another passivation alongside the cutting edge. So this can guarantee these multi-cut technologies internal loss reduce effect can be realized. And aside from that, we also introduced the polyfinger, ultra-fine metallization, carrier enhanced contact. These cell technologies. I won't go into the details of all these technology, but one point I like to mention is the polyfinger. By optimize the backside pattern of the M+ poly, we can increase another 5% of the bifaciality by adopting this technology. Okay, after introducing the how we can achieve more power density, then another two features in terms of the more power generation. The first one is the temperature coefficient. We upgrade from the previous 0.29% to 0.26%. So which means under different operating temperature conditions, as you can see from here, you can expect 0.6 to 1.5% more power generation under the ambient difference from 45 degrees Celsius to the 70 degrees Celsius. And then is the annual degradation. This is the linear degradation chart compared to the last generation. As you can see, the previous generation is 0.4%, and the new generation is 0.35%. So if you do the calculation, you can see by the end of the 25th years, so the reserved power is 3% more than the last generation. As you can see here, the new generation is 80.6%, while the last generation is 90.6%, excuse me, and the last generation is 87.2%, which means 3.4% more power is reserved for the new generation. So all those features, what I've just introduced, are pretty tangible because you can directly get this guarantee from the warranty or from our spec sheet. But I also like to highlight two features, underlying features. One is the low light performance or low irradiance performance. The other is bifaciality, bifacial gain. So because why we want to highlight these two features, because we want to say when you apply the module for the outdoor application, not only the front side power matters, but also how the module behave under different irradiance level, how the module behaves from the backside is also very critical. So on the left-hand side, what you can see is we do a side-by-side comparison with another technology route is we have the back contact. As you can see, the horizontal axis is the time, the different time throughout the day, And the curve represents that the power generation, more power generation from TOPCon versus BC. As you can see, we can get more power generation in the early morning and late afternoon, which means when the irradiance level is weak, early morning, late afternoon, you can expect more energy harvest from the TOPCon technology. And on the right-hand side is the back contact. For the back contact, sorry, is for the bifacial comparison. For the bifacial, because bifacial gain, it depends on the albedo, the ground surface, also the how you install the panel, what was the elevation or the installation method. But with higher bifaciality, you can expect around 1% more in terms of the power generation from the backside. Okay, so then let's, I will just introduce why we have these two different generation from these two aspects. So first is the low light performance. Some fun fact that you might not know that for the module, actually the front side power, the nameplate power is tested and under the STC condition, which is the irradiance level is 1,000 watts per square meter. But if you look at the left-hand side, if you look the irradiance level throughout the day, you can see that only at the noon, very short time, that the irradiance peak can reach this high irradiance level. But the rest of the time, the irradiance level is lower than this number. So which means most of the time, the module is operating under the irradiance intensity lower than 1,000 watts per square meter. And if you look, that's for the irradiance level within the day. But if you look at the right-hand side of the slides, it's different locations around all across the globe. As you can see, around different locations, we can see that only the red part, the right bottom bar chart, the red part represents the irradiance level is higher than 1,000 watts per square meter. But as you can see, the bar chart, it only represents a very little portion. It's less than 10%, which means 90% of the time, the module is operating under 1,000 watts per square meters irradiance level. So which means how the module really perform or behave under such a low irradiance situation would be very critical for the actual power generation. So under this fact, and then why TOPCon has better low light performance? So it's due to the cell architecture difference. So it's related to another factor is in terms of the leakage current. If you can control the leakage current to a low level, then you can have higher low light or low irradiance performance. And then for TOPCon, why it has better low light performance? Because its leakage current is lower than back contact. Because why we have this difference? Because of the cell's architecture difference. If you look at the upper left corner, so if you see the comparison between TOPCon and BC, for TOPCon, the NP and the different electrodes are on both sides of the cell, which means if you want to have the leakage current, it's only come through the edge of the cell. You need to pass across the entire wafer thickness. So it's hard to have the leakage current. But for back contact, the NP electrodes are all at the same side of the cell. And also they have more than 200 lines of the electrodes. So which means if you want to do the full isolation between the NP electrodes, it would be pretty hard. And then the leakage current would be inevitably higher than the TOPCon. Another point is because back contact also they need to control the hotspot issue. So they also intentionally create some leakage current channel, which will further increase the leakage current. Then if you look at the upper right hand, so we do the test. So we add a voltage bias, 12 volt bias voltage on the different solar cell. We can see that the TOPCon leakage current is 0.05 amps, but for back contact is 2.5 amps, so which is 50 times more than that of the TOPCon. And then this higher leakage current, here we have a quite complicated formula, but it's a solar principle. Well, directly calculated into this line on the right lower corner. You see the line that the BC, the low light performance will be relatively lower than that of the TOPCon, especially when the irradiance level is 200 watts per square meter. the difference is 2 to 5% between top contact and back contact. Another point is in terms of the bifaciality or bifacial ratio. I think this is also very easy to understand. This is also because of the cell architecture difference, because TOPCon, the electrodes is on both sides of the cell, so which means the front side power and back side power difference is not very big. But for the back contact, all the electrodes is on the back side of the cell. The shading are all on the back side of the cell, so which means the relatively ratio between the front and back is relatively large. So this will lead to 10 to 15% of bifaciality difference. When it comes to the system side, the power generation difference is around 1.5%. And also we have another concept is the overall efficiency comparison. If you look at this bar chart on the left-hand side, we compare TOPCon generation 3, 655 watts. For the TBC, we keep it 665 watts. As you can see, the power, the efficiency, there's around 0.3% power difference. But if you count the backside power generation, so first, if you count the 13.5% of the backside irradiation, this is according to the IEC standard. So with this amount of the irradiation, as you can see, the overall efficiency is the same. But if we consider some high albedo or high ground reflectivity ground surface, then you can generate more power from the backside for TOPCon. Then the overall power or efficiency for TOPCon would be higher than back contact. And then we keep all this in mind that we compare the TOPCon and back contact for some empirical or outdoor real testing. So this is one project performed in China. So as you can see from the picture here, this project, the installation tilt is 40 degrees. Also, you can get pretty much quite a lot of readings from the backside. So which is pretty in favor of the backside generation. So in such conditions, TOPCon has a 2.9% more power generation than back contact. And the next slides, we also do another test. Is on a low tilt roof. The tilt angle is only 10 degrees. So with this difference mainly comes from the low light performance difference. So we still can see that there's a 1.86% more power generation from TOPCon. So this generation is mainly coming from this the low light performance advantage. And then this is also another data. This is also not Trina's in-house data. We just cited this information from a national level demonstration platform. We think this data is pretty representative or has high value to refer to, because this is a megawatt level comparison. For each technology, they build megawatts level block to compare how each technology performed under the real block level or megawatt level performance. And then we can see that for TOPCon, it shows the best performance comparing to the last generation PERC. It has 2% more power generation compared to back contact. It has 1.43% power generation. So this data is also 3 years test duration. So we think this data also verify the advantage for the TOPCon technology. And then lastly, when we convert these advantages on the system side, what would be the value to the customer? So first, we compare the same size module size, different module. As you can see from here, for TOPCon G3, we have 50 watts higher than G2. For the back contact, it's still 10 watts higher than our G3. As you can see from the bar chart on the right-hand side, the BOS, the TBC has the most savings, but because of the more power generation from the TOPCon, as you can see from here, the TOPCon will have more revenue in terms of the power generation. Then in the overall comparison, the TOPCon G3 compared to the TBC can have 1.5% LCOE reduction. Then we also compare our Trina's large format flagship modules with the TBC as well. Not only for this one, not only we have benefits in terms of power generation, but in terms of BOS, because large format module, you can significantly reduce the BOS. The BOS would be the best as well. compared to TBC, then the overall power LCOE saving is more significant. It's 1.8%, 82%. And then we also perform all different similar studies across the globe in different regions, Europe, Middle East, China, APAC, Australia, and Latin America. We all see that TOPCon 3.0 can deliver more value in terms of the large ground mount power plant application scenario. So the value is around 0.6 to 2 US dollar cents per watt. Okay, lastly, quick summary that for our new generation G3, first we can deliver more power on the same size, 15% more, 15 watts more, but also we can deliver more power generation from the lower degradation, better temperature coefficient, but more importantly, the higher bifaciality or superior low light performance can also outperform other back contact technology routes in terms of the overall system performance on the large scale utility ground mount application. So, okay, so that's all. That's everything for my presentation. Thank you.
Thank you very much, Rocky. That was very, very insightful, very detailed. Thank you. So got a little bit of time for a few questions. So I'm just sort of summarizing some of the ones that have come in. There were quite a few regarding the section there. You were talking about the performance of your TOPCon modules versus back contact. Seems to be some interest in that particular area. I'll just sort of wrap a few of these questions together. I think you may have gone over this quite quickly, but the first question, can you recap on the percentage of low light gain that you see in your TOPCon versus back contact? I think there are a couple of different figures that you briefly went over there, but perhaps just as we've been asked about this, if you could just remind us of those. Also, is the low light data that you discussed here captured in .pan files for PV-SYST simulation? A couple of questions there on the relative performance against back contact.
Yeah, so for this question, the back contact and the TOPCon, the low light performance, when the irradiance level is 200 watts per square meter, the difference would be 2 to 5%. But when it comes to the system side or the real application, what would be the overall power generation difference? It depends on the location. Different location, different irradiance level, right? Different weather conditions. So this number would be vary. But I'd say according to our simulation, the difference would be 0.5 to 1%, more than 1%. The additional contribution from the TOPCon technology versus back contact.
I see. Okay. Yeah. And on the question there about the data, some of the data that you've obviously gathered on this, is that available for the purposes of simulation in systems such as PV-SYST?
Yes. It depends on the pan file, which version you're using, right? So, but I say from the actual physics difference perspective. So there's a difference here, but depends on the pan file you're using. You can expect some additional power gain for the low light performance for the.
Okay, all right, thanks. And just to be clear, was the data you were presenting there, was that lab test data, or was this sort of real test case scenarios that you drew this from?
We offer you 3 real test data. So 2 within Trina. One is we cited some information from the national level testing platform. So we see the overall power generation is among 1.4 to 3% more for the TOPCon. So that's the real-time testing data. And also for the case studies at the very end, I presented is Trina's assessment based on the PV-SYST, and that based on CD-SYST, we also have around 1.5 to 2% more power generation. We reflect this number, which is in line with the real applications situation. Then we reflect this number to see how much additional value on the system side. So we get this around maybe 0.5 to 2 euro cents, up to 2 euro cents additional per watt, additional value on the system side.
I see. Okay. Couple of questions here, which I'll again sort of group together, just about performance in different sort of conditions. So one gentleman asking about, and I guess this is something we hear a lot about, discussed in sort of PV module and system performance at the moment around hail. You know, hail is obviously becoming a real consideration for for the industry all around the world, but you know, in certain markets, especially such as the US and such like. But can you talk a bit about any measures in this technology, in this new product, to reduce vulnerability to sort of extreme weather damage such as hail? Related to that, there's a question about mechanical performance. I guess it's a sort of slightly tangential question, but similar. I think mechanical performance of modules is quite a big talking point in the industry at the moment, you know, with spontaneous glass breakage and such like. So two sort of related but distinct questions there. I wonder if you could just talk generally about the sort of yeah, the performance of your modules in those sorts of situations.
Yeah, it's a very good question. Actually, for Trina, we can optimize our product configuration based on the actual application scenario. For our standard product, for the standard moderate climate, we can offer the standard version, but also for some hail-prone regions with larger hail impact or threat, we can offer also enhanced structure, like we can change the cell, so the glass from 2 plus 2 millimeter to the 2.5 plus 2.5 millimeter tempered glass, and which can further enhance the hail resistance. It depends. At the end of the day, it all depends on the project, on the situation, on the application scenario. We can tune our BOM and our different configuration encapsulation to guarantee that the module is reliable for different application scenario.
I see. So I guess adaptability is the kind of key feature there. Great. Okay. Just in terms of application, I mean, we've been talking, and I think most of your presentation there was largely discussing your modules in the context of the utility scale segment, but obviously rooftop as well is a significant and likely sort of growing part of the industry. What's your sense of you know, the sort of suitability of this technology for rooftop, or are there other technologies that you think are better suited to rooftop that you know, we might see applied in that context going forward?
So very good question. So for Trina, actually, I think what I present today is mainly for the large-scale ground-mount power plant. So we believe for these application scenarios, especially for the dual side, the front and back side power generation scenario, which represents 80% of the overall market. So we believe TOPCon will be the mainstream. Now we have G3. In the future we'll have G4. But for the rooftop application, we also have another technology. We acknowledge the back contact. We'll have some also have some advantage. So that's the reason why Trina, we also introduced another new technology, is THBC. We also break the world record last month. So THBC is a TOPCon compatible hybrid back contact. It's hybrid TOPCon with hydro junction with the back contact altogether. Compared to the current industrial TBC, it can have additional 10 to 15 watts power increase. So which means that it can further increase the monofacial application scenarios, power density and power increase. So on that scenario, Trina will also on that directions.
I see. Thank you. There's a quite specific question here. You may have covered this. There was quite a lot of data that you went over, but is there a significant change in the open circuit voltage and short circuit current with this new technology?
No, it's the same. It's the same with the last generation, similar range. It will be very compatible for the electrical part with inverters or other electrical components, and also mechanical part. The module dimension is basically the same, so you can expect a very compatible set of module on the system side.
I see. Question about the production of the new module, the large format one. Can you give a sense of the expected mass production level for, that you're anticipating for the new large format module?
It's for medium and large format module. It's all from this year's Q3. And also one thing to mention that for Trina, we have 25 gigawatts for these two modules, so which means a very sufficient capacity. If you have any requirement, you can reach out to us. We can supply.
I see. Okay, great. Well, I think I've pretty much been through all the questions there and thrown in a couple of my own. So I think we've, I mean, there were quite a few detailed questions about specific sort of environmental conditions, but I think you dealt with that where you were talking about the sort of optimization for different circumstances. I mean, actually, I'd say that is probably the theme of questions that we've had most. So is there anything you would want to add to that about the sort of adaptability of this module technology for different environments, different applications as well? I mean, obviously, sort of scenarios such as data centers, desert installations, all of those kind of things are quite relevant at the moment. So I don't know if you've got any other comments you'd want to finish on about the sort of optimizability, if that's a word, of this module for those different applications.
Yeah, for Trina, we have 4 capability for the more variety or adaptability for the module. For data center, for this application scenario, data center, the asset value is very high. So we can offer you more enhanced configuration in terms of the anti-fire rating or better protection or durability. So we can all do that.
Great. Well, thank you very much, Rocky. Some great insights there. That brings us to the end of today's webinar. I hope you've all found it informative, insightful. I certainly have. I think what we've heard today just underlines the extent to which, as far as PV has come in the past 20 years, continued technological evolution still remains at the heart of its onward journey towards becoming the world's most important form of power generation. A few of you asked about availability of materials from this webinar. There'll be a full recording of it available soon on the on-demand section on PV Tech, and I believe the presentation will be circulated to those who've signed up today once we're done. So keep an eye out for that. I'd like to offer a huge thanks to Rocky, our speaker today, for educating us on this important topic. And of course, I'd also like to extend a big thanks to Trinasolar for sponsoring this webinar, and for everyone, of course, who's worked behind the scenes to make it happen today. From me and the PV Tech team, thank you again for tuning in. We appreciate your attention and ears. Have a very good rest of your day wherever you are. Thank you, and a very warm goodbye. Thanks a lot. Well.